Our first speaker is Neri Continetto. Neri, can you please share your screen and turn on your microphone and your camera? I can see you there. Neri is from the University of Western Australia.
I've included them in here.
Their talk is titled Measuring Hydrodynamics and Sediment Resuspension in Coastal Canopies.
Yeah.
Hi, Elena, thank you. Hope you're all hearing me well. My name is Neri Continetto. I study sediment dynamics and hydrodynamics in seagrass meadows. I think the first question that people would be asking is why I'm talking about seagrass meadows in a coral reef symposium. But the first answer will be, in terms of ecology, they are related environments. They often occur in a proximity or with an ecological link in between the two. But what we actually study is the fluid dynamics. So I would like you to remember this instrument here in this picture, which is pretty much like 6 centimeters in diameter. And I'll be explaining about it later on. So as I said before, coral reefs, seagrass meadows, mangroves, and kelp forests, we all encompass these benthic environments as canopies, which we define as a high bottom roughness environments in comparison to, let us say, a bare bed environment. So in this picture here on the right, you can see this red dashed line here represents the mean velocity profile when you have a bare bed. So if you have a pure sand with, let us say, wind-driven current, you have the maximum velocity near the top, the free stream near the surface, which logarithmically decays to the bottom. And when you have a canopy like the seagrass or a coral reef, the elements of the canopy exert drag on the flow, and which reduces the flow and interacts with the flow. And that's what we are interested in studying, what's actually happening inside this canopy, because all these environments, they're closely linked to the sediment, the underlying sediment. And the sediment tells a lot about the health of the ecosystem, and the process that happened inside it are very important to study. So the motivation to this study comes from our first paper that showed that so we had instruments measuring in the middle of the canopy and on the top of the canopy, and many studies have studied canopy only accounting for what's happening inside the canopy, but not happening. What's happening above the canopy, on the top of the canopy, but not fully understanding what's happening inside the canopy. So we try to do it by putting instruments in the middle of the canopy that measure currents and sediment in the middle of the canopy. And an important concept here is the critical velocity, which is this symbol here, this black dashed line. And critical velocity means a velocity over which, if you pass this velocity, if you have a greater velocity than this critical, it means that your sediment is suspended. So in a bare bed, which is the red colors here, you can see that passing like greater values than the critical velocity, you have a response in the sediment, suspended sediment concentration. But in a canopy, which are the green dots here, even if you have greater velocities than the critical, if you measure on the top of the canopy, this is not translated to the sediment resuspension because you're measuring on the top of that. So in conclusion from our study is that measuring what's happening on the top of a canopy, whether it's a seagrass or a coral reef, doesn't necessarily represents the full reality of it's imparted to the sediment. So another thing that we notice is that even if your velocity is high enough to resuspend the sediment, there is a structure on the suspended sediment concentration, which basically means that from bottom upwards, the sediment concentration will get smaller. That's what I call, this picture here represents what I call standard fieldwork measurements, which that's what I've done in my first paper. Most of our knowledge in canopy hydrodynamics and sediment dynamics comes from laboratory and flume work or modeling, which represents a controlled environment. You can set up your current and waves, And when you move into the field work and if you use standard instruments for field work, if you account for the size of your instrument and the frame, you end up having the first measurement on 20 centimeters from the bottom, 30 centimeters from the bottom. And if your canopy is bigger than that, you're not necessarily studying what's happening inside it. You can always flip the instrument upside down, but because of the beam spread, which is the direction of the sound that the instrument emits, because of the beam spread, you end up having to clear a big patch of seagrass. And if you want to study what's happening inside the seagrass meadow, this doesn't make sense. And also in the study of sediment, if you have a single point measurement, which is often used, you also have to clear up a patch of your canopy. But apart from that, you have only a single measurement that you account for being representative for the whole water column, but this may not be necessarily true. So what I did in my field work was bringing instruments from the laboratory into the field work, and that's the innovation of our work. And to measure currents, we use the high resolution vector that it measures at real time. So we can actually see if our data has a good quality. We would move up and down. Is that instrument that I showed in the beginning? And as it is only 6 centimeter diameter in the probe, you don't need to clear any patch of the seagrass. And also bringing the sediment profiler, there was a different from a single point OBS, a single point optical backscatter sediment instrument. Because the sediment profiler not just gives you a full profile every centimeter, you can set up this whatever you like, but it gives you a full profile of the sediment concentration. And because it has different beams, it also gives you different concentrations for different sediment sizes. The downside of that, and now I'm showing where I did my field work, is that this type of study is a bit hard to do. You need to account for a big infrastructure. As I said, as it has real data, you need to bring a laptop to the field work, and for that we needed to have scaffolding on the beach. But the idea was that if we could have a good idea of what's happening inside a canopy, people could expand this kind of studies for whatever they like, because we think that this could be helpful for ecologists, for people that are studying nutrients in canopies, or people that are only studying sediment, and they don't need to do like a full picture of the flow structure over a canopy. So we chose the site because Rottnest Island, offshore Perth. We chose the site because it's a mixed site where both waves and currents are important, and we wanted to have a big variability into that. A bit of the instruments here, the ones here on the right represents what I called before the standard fieldwork measurement, and on the left are the instruments that we brought from laboratory. So the PIV is a camera that takes 25 pictures per second, and also we had a high resolution vector, the one that I mentioned before, measuring currents and waves at 25 data per second, 25 hertz. And we could compare different instruments, but not just compare, but also one will be adding information to the other for our study. Moving to the results now. The left-hand side panel here means the mean current profile. The y-axis is the height above bottom. This gray area here represents the height of the seagrass in our site, which is roughly 30 centimeters high. And the x-axis represents each velocity point in the time average velocity at each height divided by the free stream velocity, which is the one that I said before. Is the biggest velocity, which is the one near the surface. And these black dots here represent the standard instrumentation. So you can see the logarithmic shape that I mentioned in the first slide. And in terms of the structure of the flow, first of all, sea swell and sea waves, they are roughly the same amount of importance for the site. And you have an expected decay in turbulence inside the canopy. when we brought the laboratory instrumentation, we had a whole different world because, well, first of all, near the top of the canopy, we had a result of roughly 10 centimeters per second and at 25 centimeters from the bottom. But because of the laboratory instrumentation, we could have a very good measurement at only 2 millimeters from the bottom, which usually people can only get in laboratory work. And because of that, we saw a massive reduction from 10 centimeters per second of mean current to 1 centimeter per second. And this, I'm talking about only almost 25 centimeters high. And so it's a big reduction. And in terms of the structure of the flow, you can also see that, well, the blue line representing the top of the canopy and the red line, the near bottom velocities and flow. We saw that swell waves are much more attenuated than sea waves that are more attenuated than turbulence. And not just that, but compared to what's happening inside the canopy, above the canopy, the turbulence accounts for, it's relatively more important than inside the canopy than it is above. And this has a very important ecological aspect because of nutrient uptake, that there are many articles on that. And so not just the critical shear stress is important for sediment dynamic, but also turbulence might be important depending on the density of your canopy. In terms of the suspended sediment concentration, this is the optical backscatter that it's linked here on the bottom, the bed shear stress. We could see the red line as being the critical bed shear stress. So every time our shear stress was bigger than the critical shear stress, you could see a result in the optical backscatter as it is expected. But the good thing that we saw by using laboratory instrumentation into that field work is that we had different grain sizes, concentrations. So I'm only showing two beams here, one for 200 micrometers and another one for 100 micrometers. But there is a homogeneity on the concentration of 100 micrometer particle that we didn't see in the 200 micrometers. So near the bottom, there's a bigger concentration of 200 micrometer particles that are attenuated upward. And this wouldn't be possible without the laboratory work. This whole work actually wouldn't be possible without bringing this laboratory instrumentation. And just to wrap it up, the core messages of this is that up to 90% of the velocity is attenuated from the top of the canopy to the bottom. Attenuation is dependent on the frequency of the flow that you're studying. So swell waves are more attenuated than sea waves that are more attenuated than turbulence, which increases the importance inside the canopy. And finally, there is a structure on the sediment concentration according to the sediment size due to the canopy characteristics. So thank you, and I'm open for questions now.